This is the second part of the lecture on understanding basic inferential statistics. For the first part of this lecture, we're going to take a closer look at what we mean by factorial designs and how we can interpret the independent or separate effects of each independent variable on an outcome measure, and then the combined or interaction effect of the two independent variables together. For the example that I'm about to present, I'd like for you to refer to a handout in which there was an article summarized about how loud music can make people drink more in a bar. The hypothesis that was tested is whether or not loud music could make people drink more. Drinking more tends to mean more profits for the bar that is serving the alcohol. So in this study, the alcohol consumption was studied at two different levels of music. And as predicted, when the music was loud, more alcohol was consumed. So I would like to take the idea of that study and continue it a little bit as we look into the interaction effect. What I'd like for you to do is pretend that we're doing a study in which we are simultaneously analyzing the effect of music volume, which would have two levels, normal and loud, and then also the effect of gender, that is, male and female, on the amount of alcohol consumed. So you should have a handout that has a table of data and then corresponding graphs of data in which you see A1, A2, and B1, B2. On this handout, there are three separate hypothesized outcomes. In the boxes, you see values ranging from 0 to 40. Let's assume that that represents the outcome or dependent variable of alcohol consumption. In the first example, what you see across the top in the table is A1 and A2. I want you to think of A as the music volume variable. A1 is normal, A2 is loud. On the side of the table, you see the levels B1 and B2. Let's assume that B is the independent variable that represents gender. In this case, we're going to let B1 represent female and B2 represent male. In the first series of data, we see the box says 40, 40, 20, 20. That is the combination of normal music and male, has a value of 40. The combination of loud music and male has a combination or value of 40. The combination of normal music and female has a value of 20, and the combination of loud music and female has a value of 20. In order to determine the main or independent effects of each independent variable, what we're going to do is look at the means, going down the columns and then across the rows. So in this particular table, it's been done for you. Looking down at the overall averages for the two levels of music volume, we see that the mean for normal volume is 30 and the mean for loud volume is 30. What that means is, regardless of gender, the overall mean for alcohol consumption is the same for loud and normal music. Thus, we would say that there is no main effect of music volume because the averages for the loud and the normal condition are the same. If we look across at the two levels of gender, again, B1 is female, B2 is male, you will see that the overall average for B1 or female is 20, and the overall average for B2 is 40. Thus, there is a main effect of gender. Men drink more than women in this study. So that is regardless of the music volume. Men drink more than women. So far, based on the results of the first study, there is no main effect of music volume. There is a main effect of gender. To ascertain the potential third effect, the interaction effect, what we're interested in determining is whether or not the values for the second independent variable are different at the different levels of the first independent variable. In other words, does the difference between males and females change for loud versus normal music? In order to help us ascertain the interaction effect, we're going to look at the graph. The graph makes it much easier for us to tell. The general rule is if you graph the data and the lines are parallel, there is no interaction. Let me say that again. If you graph the data and the lines are parallel, there is no interaction. What that tells us is that the difference in the values across the level of the first independent variable are the same across the levels of the second independent variable. To understand that better, let's take a look at the first graph. What you see are the lines representing B1 and B2, that's gender, across the levels of A1 and A2, that's music volume. So if we look at A1, we see, again, males have a value of 40, females have a value of 20. The difference between males and females during normal music volume is 20. If we move over to A2, which is the loud music volume condition, the difference between how much the men drink and how much the women drink is also 20. The difference is 40 versus 20. So here we have no interaction. The difference between the amount that men and women consume is the same for normal music volume and loud music volume. So the final conclusion from the first example is that there is no interaction between music volume and gender. Let's take a look at the second example. Here the values in the cells are a little bit different. The value for the A1-B1 combination is 0. For A2-B1 it's 20. For A1-B2 it's 20. And for A2-B2 it's 40. So let's first assess the main effect of music volume and gender. If we look at the effect of music volume first, that's independent variable A, the average, the overall average for the normal volume condition, that's A1, is 10. The average for the loud volume condition, that's A2, is 30. So here we have a difference. Under normal music conditions, the average is 10 ounces. Under loud music conditions, the average is 30 ounces. Thus, we have a main effect of music volume. Looking at gender, the overall average for females is 10. The overall average for males is 30. So again, there is a difference. Overall, men drink more than women. It's a difference of 30 versus 10. So we would say that there is also a main effect of gender for this example. Now, when I say main effect, it doesn't mean that we can say conclusively that there is a significant difference. That would require actually conducting an analysis, such as a t-test. But at least we can say here descriptively that there is a main effect because there is a difference in the outcome variable between the two levels of the independent variable. The last possible effect, again, is the interaction effect. So let's take a look at the graph because that's the easiest way to determine whether or not there is an interaction. If we look at what is going on at A1, that is the normal music volume, we see that men drink 20 ounces and women drink nothing. Okay, those are the results of this study. The difference between how much men and women drink under normal music volume conditions, or A1, is 20. Moving over to A2, which is the loud music condition. Again, the difference between the amount that men and women drink is 20. In this case, men drink 40 ounces, women drink 20 ounces. But what we're looking at is the difference between men and women. So here, again, we have no interaction. The difference in the amount drank by men and women is the same under normal and loud music conditions. To put it simply, the lines, again, are parallel. There is no interaction. Let's take a look now at the third example. where we have values of 20 for A1 and B1, values of 20 for A2 and B1, a value of 20 for A1 and B2, and a value of 40 for A2 and B2. Now this should come a little bit faster. Let's take a look first at the overall or main effect for music volume. Under normal conditions, which would be represented by A1, the mean is 20, and under loud conditions, the overall average is 30. Thus, we have a main effect of music volume because the averages are different between the normal and loud conditions. With respect to gender, again, we have a difference. For females, the average consumption is 20 ounces. For males, the average consumption is 30 ounces. So there is a difference between level 1 and level 2, representing male and female. So we also have a main effect of gender. To assess the possible interaction effect, let's take a look at the graph. And here we begin to see something a little bit different. Notice the lines are not parallel. Under the normal music conditions, that is A1, both men and women drink approximately 20 ounces. But when we move to A2, or the loud music conditions, you will notice that there is a widening. There is a difference between the amount that men and women drink. Here, women drink on average 20 ounces, men drink 40 ounces. So in this example, we have an interaction effect. The difference between the amount of alcohol drank by men versus women is different between the normal and loud conditions. To put it more simply, the difference between the amount that men and women drink is more for the loud music condition than for the normal music condition. So there are several ways to state the interaction effect, but basically, men drink more than women when the music is loud. Men and women drink about the same when the music is of normal volume. What that tells us is that there is a gender difference, but only observable during a loud music condition. You have another practice handout. It is called Factorial Designs Practice. And I'd like for you to take a look at that one next. In this one, we have some hypothetical results, and you can read the purpose of the study at the top of the sheet. We have the effect of sense of humor and gender target, on perceived attractiveness of potential mates. So in other words, we have two potential variables here. Participants were told whether a picture that they were looking at of the person had either no sense of humor, an average sense of humor, or a good sense of humor. And then the person was either male or female. So these two factors were studied with respect to potential attractiveness. Attractiveness was evaluated by the opposite sex. Sense of humor has 3 levels: none, average, and good. So, in the first instance, we have hypothetical results with sense of humor and target gender listed. For this example, if we look at the potential main effects, the overall average for male would be 3. The overall average for female is 4. Thus, there is a main effect of gender. If we take a look at the overall averages for the 3 levels of sense of humor, the none condition has an overall average of 1.5. The average condition has an overall average of 3.5. And the good condition has an overall average of 5.5. So again, there is a difference in those average values across the 3 conditions. So we would also say there is a main effect of sense of humor. In order to determine the possible interaction, we would look at the graph of the data. Clearly, these 2 lines are parallel. So the difference in rated attractiveness between men and women is the same across no sense of humor, average sense of humor, and good sense of humor. It looks like overall, females are rated a point above males across all of the conditions. So here we have no interaction. Under the second set of hypothetical results, the overall average for males is about 4.3. The overall average for females is about 2.6 or 2.7. So we do have a main effect of gender. If we look at the averages for the different levels of sense of humor, the none condition has an average of 2.5, average has a mean of 3.5, and good has an average value of 4.5. So again, we have a main effect for sense of humor. Now let's determine the potential interaction effect. And you see that something kind of unusual is going on in the graph. The difference between the ratings for men and women is about 1 point under the none condition and 1 point under the average condition. But when we get to the good sense of humor, suddenly males are rated on average 3 points higher than women. So the difference between the ratings for gender has changed under the good condition compared to the other conditions. So one way to interpret this information is to say that males and females differ most for the good sense of humor condition. That would explain what we mean by the interaction in this case. So the lines are not parallel, and the difference between the ratings for men and women is greatest for the good sense of humor condition. For the last set of hypothetical results, the difference between the averages for men and women is essentially none. The average for males is 4. The average for females is also 4. So there is no main effect of gender. If we look at sense of humor, the average for none is 4, the average for average is 4, and the average for good is 4. So there is no main effect of sense of humor. So far we have a hypothetical result in which there is no main effect of the first independent variable and no main effect of the second independent variable. But if you take a look at the graph, something very interesting is happening. And this is the potential benefit of a factorial design. A factorial design will uncover a potential interaction effect despite the fact that there are no main effects of either independent variable. If you take a look at the graph, you will notice that there is a complete reversal in the data. Under the no sense of humor condition, females are rated higher. But under the good sense of humor condition, males are rated higher. And that would probably be the best way to interpret this interaction. So yes, there is an interaction, and the easiest way to say it is that females are rated highest under the no sense of humor condition, and males are rated highest for the good sense of humor condition. So in this case, not only do we have lines that are not parallel, we have what's called a complete interaction, where the lines actually make an X on the graph. So the hypothetical results 3 are the most unusual, but also the most important with respect to factorial designs. A factorial design would allow us to uncover an interaction effect even when no main effects are present. That's something you could not do if we would do a separate analysis on gender and a separate analysis on the effect of sense of humor on the perceived attractiveness. I want to switch gears a little bit and go back to the handout on understanding basic inferential statistics. Now we've gone through examples of factorial ANOVAs and how to interpret both main effects and interactions. Remember that you can have any possible combination of effects. You can have just one main effect, you can have just 2 main effects, you can have 2 main effects and an interaction, just 1 main effect and an interaction and no main effects. In other words, it is not required to have a main effect in order to have a significant interaction. These are all independent effects on the dependent variable, and any combination is possible. Of course, the possibility exists that you would have no effects whatsoever, but we hope that in our data that would not happen. The last part of the sheet on understanding basic inferential statistics has to do with those statistics that are used to evaluate relationships between variables that are not cause and effect. The most common one that you see and that you're probably familiar with is a correlation. Correlations are designed simply to assess the natural relationship between variables. A cause and effect relationship is not implied. We simply collect data on variable 1, collect data on variable 2 for each subject, and then determine whether or not they are significantly related to each other. The most common type of correlation, again, is known as the Pearson correlation. This analysis is most appropriate when both variables are numerical. In other words, they are scores or some kind of number value that are truly on an interval or ratio scale. We have two types of correlations, one positive, one negative. A positive correlation means that as the values of one variable increase, so do the values of the second variable. In other words, the variables travel together. They either both go up or they both go down. They move together. So the example that you see is that as sun exposure increases, the number of wrinkles increases. So presumably as one goes up, so does the other. The other type of correlation is known as a negative correlation. That means as the values of one variable increase, the values of the other variable decrease. So the example on your sheet, as consumption of some diet aid called Fat Blaster 3000 goes up, weight goes down. That would be a negative correlation. The next type of correlation listed is one that you might not be familiar with, and this is called a Spearman correlation. This correlation is appropriate when both variables are ranked. That is, both variables are on an ordinal scale of measurement. So it's very easy to pick out when a Spearman correlation would be appropriate because there has to be some indication that both variables are ranked. So on the example that you see, there is a relationship between a student's class rank and the rank of the graduate programs to which the student chose to apply. So here again, both variables are ranked or on an ordinal scale, and this is when you would use a Spearman correlation. The next type of correlation is known as a point biserial correlation. This type of analysis is used when one variable is numerical, such as a score or any variable on an interval or ratio scale, and the other variable is what we call dichotomous. That means the variable can only take on two possible levels. An example of a dichotomous variable, just generally speaking, would be gender, male or female. It would also be a response to a question, yes or no. If the possible values can only take on one of two levels, you have a dichotomous variable. So for example, there is a relationship between on-the-job training and work evaluation score by a supervisor. Either people have had on-the-job training or not. It is a yes or no variable, making it dichotomous. But work evaluation score is a continuous variable. It's rated on either an interval or ratio scale depending on how it's measured, but it is truly numerical. So a point biserial would be appropriate when one variable is numeric and one variable is dichotomous. In other words, it can only take on one of two possible levels. The phi coefficient is another special type of correlation in which both variables are dichotomous. That means both variables can only take on one of two possible levels. So the example that you see is that there is a relationship between having siblings and personality type, here measured as introvert versus extrovert. So there's only two possible levels of having siblings, either you do or you don't. And there are two possible levels of personality type here, introversion or extroversion. So a phi coefficient is appropriate to assess a relationship in which both variables are dichotomous. Building on that idea is the last analysis that you see on the sheet, the chi-square test. The chi-square test is used when both variables that you are trying to relate are categorical. We would call that discrete. They can be larger than dichotomous. In other words, one of the variables could have 3 or 4 or 5 or more levels. So think of a chi-square test as a larger version of an analysis that would use a phi coefficient, because it allows the possibility that either one or both of the variables have more than 2 levels. So the example on the handout is that there is a relationship between birth order and type of schizophrenia. There are several different types of schizophrenia, and there are also several different birth orders. Most commonly, birth orders are evaluated as first, middle, last, or only. So both variables can take on several potential levels, and this is the case in which a chi-square test would be the most appropriate. This concludes the lecture on using statistical analyses. And now you should be able to apply what you have learned for any type of research design.